Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This video and the others in the Chapter 6 Problem Solving with Python playlist are an introduction to the concepts you will need to write programs with lists. This video accompanies Problem Solving with Python Chapter 6, but it's okay if you don't have the book. The videos stand alone as instruction on these topics. In the last video, we talked about some list operations, including append, remove, insert, count, index, and the in operator, plus a few more. In this video, we're going to talk about using a loop to iterate over a list, visiting and processing every element, and we'll revisit some of our loop algorithms. Let's dive in. I have here a program called basiclistloops.py, and in it, I've defined a list called inventory. You might recognize it from our prior list videos with a few extra items. It contains the following strings: key, potion, Python book, apple, coin. Recall that we can refer to the entire list by its name, inventory, but to process individual elements, we use the indices of the elements. Indices begin at 0 and proceed in increments of 1 to length of the list minus 1. This list has 5 elements, so the indices of the elements in this list are 0 through 4. 0 through the length of the list, 5 minus 1. Very often when we have a list, we want to process each element in the list one at a time. We usually don't know exactly how long our list is, so we need to write general code that will process our list regardless of its length. Fortunately, this is easy to do, and once you learn this pattern, you can reuse it for any list processing code. Let's write a loop that will print each element in our inventory one to a line. I'll write a comment, show the player the inventory. Now think about what that looks like. We want to print inventory sub 0, print inventory sub 1, print inventory sub 2, and then inventory sub 3 and inventory sub 4. When we're writing a loop, we look for patterns. What's the same for each iteration of the loop, and what's different? And what pattern do the differences follow? What is the same here is that we are printing an element of the list each time through the loop. What is different is which element we're printing, the index of the element. And the pattern is that the index begins at 0, ends at the length of the list minus 1, and increases in increments of 1. So to write a loop to do this, we need to have a variable, index or I for short, which will be 0 the first time through the loop, then 1 the second time, up through 4 the last time. So we want a stepper variable starting at 0 and ending at 4, changing in increments of 1. Let's annotate a variable I of type int. We can use a while loop or a for loop to do this. A while loop can tackle any looping task, but a for loop is preferable when we know in advance how many times we want the loop to execute, because it's more readable. All the control information is in the header line of the loop, and there's less code, no initializer and updater, so less opportunity to introduce an error, and easier to modify. We know we want this loop to execute list length times. And note that a default range generates the indices of a list. Range 5 generates 0 through 4 in increments of 1. Range 10 generates 0 through 9 in increments of 1. The range function is designed to help us iterate over a list using the element indices. That looks like for I in range len inventory, colon, for the for loop header, and then in the loop body, here we're going to print each element in the list, so print inventory sub I. Let's unpack that. Remember, we want to visit inventory sub 0, inventory sub 1, inventory sub 2, inventory sub 3, and inventory sub 4. Inside the loop, we're visiting inventory sub I. So I needs to be 0, then 1, 2, 3, 4. We've written ranges to do that. That's range 0, 5, 1, where 0 is start, up to but not including 5, the stop, in increments of 1. We can write that as simply range 5 because 0 is the default start and 1 is the default stop. But we don't want to hardcode the 5 or use a literal 5 in other words, because we want to write code that will work for any length list. If we add to the inventory by picking up an item, or remove from it by dropping, using, or losing an item, we'll still want our printing code to work. So instead of passing 5 to the range function, we pass len inventory, which will be 5 if the inventory contains 5 items, but it will be 4 if it contains 4 items, and 10 if it contains 10 items. It will always be the correct length of the list. This is a pattern you can always use to write a loop that accesses every element of a list. For I in range len, the list name, and then within the loop, list name sub I. This is a powerful pattern because not only can we access each element, we can access the location in the list. So let's say we want to change the elements in the list. This pattern will allow that. Imagine we've had a spell put on our inventory that turns everything in the inventory into a toy version of itself. Let's write that code. So I'll write a comment. Replace every inventory element with toy plus element. Then I'll use the same pattern for I in range len inventory, colon, but now inventory sub I is going to be on the left side of an assignment statement. Inventory sub I equals toy plus inventory sub I. Remember how assignment statements work, right to left. So we'll first access what's currently stored in inventory sub 0, or what inventory sub 0 evaluates to, which is key, and we'll prepend that with toy on the right side of the assignment statement, giving us toy key. And then that gets assigned to the variable on the left, inventory sub 0. This replaces inventory sub 0 with toy key. And then in the loop, we continue and do the same for all elements of the list. Let's copy the print code and print the inventory again, but let's put a blank line above it to separate this visually from the output of the earlier print loop. And let's run the program. And it prints our inventory items one to a line, and then after replacing them all, it prints the new toy inventory items one to a line. Now I want to show you another pattern that's less powerful, but also less prone to error. What I'll do is replace the printing code when we print the second time. Instead of looping over the indices 0, 1, 2, 3, 4, I can loop over the elements themselves. The elements are of type string, so I'll annotate a variable called item of type string. And then I'm just going to delete this loop to avoid confusion and write the new one. For item in inventory, colon, and then indented print item. When I run the program, you'll see the output is the same. A for loop can use any collection type for the argument after in, including a list. We've used a range up until now. So the loop control variable, item, is going to be key, the first time through the loop, potion, the second time through the loop, Python book, the third time, then apple, then coin. Now, this is less prone to error because there's no way you can create an index out of bounds error if you accidentally get your range incorrect. You shouldn't get your range incorrect if you use the pattern above, but suppose you don't use the pattern because you're doing something slightly different, then there's a chance you'll have a range error. This pattern always visits each element in the collection in order. But it's less powerful because we don't have access to the location of the element, only the element itself. So I can't change the list. I can only do something with each of the elements, such as print them. For many applications, that's all you need. My recommendation is to choose this pattern if you're using the elements of a list, such as totaling them, if they're numbers, or printing them. And then choose the other pattern if you need to modify the elements of the list, such as scaling the values if they're numbers, or appending to them if they're strings, as we did before. Maybe you would want to replace them with all uppercase or all lowercase versions of themselves. Anytime you need to change them, you need to use the for I in range len list pattern. Now, before we go, let's revisit some of our loop patterns from before and show how they work the same with lists. I'll include a link to the loop patterns video if you haven't watched it or if you want your memory refreshed, because I'm not going to go into a lot of detail with the patterns. The patterns are the same. I'll just demonstrate them using lists rather than input from the console or a file. We saw patterns for totaling values in a list or accumulating them, and patterns for finding the best fit value in a list. We did this by defining variables to hold the accumulated value and the best fit value. Because I think this is easier to understand with integers, let's create another list, a list of integers. Let's pretend there is a tavern game with dice in it to stick with our adventure game theme. And to play, the player rolls 5 six-sided dice. So I'll annotate a list called dice of type listInt. And let's comment out the inventory code so we can focus on our list of dice and the most wanted holder and accumulator patterns. So I'll select the inventory code and choose Comment Out Region from the Format menu. Now, with our list, we could just hard code some die values in there, but to make it more fun, I'm going to import random and randomly generate the values in this list. I'll comment roll the dice. Now, here's how I'd randomly generate a roll for the element at index 0. Dice sub 0 equals random.randint 1, 6. Pause the video and see if you can write code that will initialize all 5 elements of the list using a loop. I'm not sure if that was a trick question. If we initialized the list to contain 5 values, such as 5 zeros, then we could use our pattern for I in range len dice to access each element and replace it with a random value. Or we could initialize our list to the empty list, dice equals open square bracket, close square bracket, and append 5 values to the empty list. It's fine if you did it the other way, gave it 5 zeros, and then replaced them, but I think appending here is fine. So I'll write for I in range 5, and then dice.append random.randint 1, 6. Let's just print and see what our values are. So I'm just going to print dice rather than writing a loop because this is just temporary code. And let's run the program a few times. And you can see each time we get 5 different values between 1 and 6, representing the faces of 5 dice. Okay, we have our list of 5 integers, our dice. And I'm going to leave the temporary printing code in so we can confirm that our accumulating and most wanted algorithms are working correctly. Let's pretend that there are 2 ways to win this dice game. The first is this. The tavern keeper rolls 1 die, and the player with the most rolls of the same die also wins. So if the tavern keeper rolls a 3, you need to count up your 3s, and the player with the most 3s wins. Let's implement this. Remember, to total, we'll want a variable in an accumulator roll, and we can call that variable count because we're using it to count up or total up the number of die that match the tavern keeper's die. I'll annotate count of type int. We'll also need to generate the tavern keeper's roll. We can call that winning number, so I'll annotate winning number of type int. And then we'll generate winning number equals random.randint 6. Above that, I'll put a comment, play the tavern dice game. Now, with an accumulator, we need to start it out with an initial value, and each time through the loop, we add something to it. Sometimes that's the most recent holder, if we're accumulating a total, and sometimes it's 1 if we're counting. Sometimes it's something else. Because we're adding, we want to start with an initial value of 0. So under my comment and the code that generates winning number, I'll write count equals 0. Now, which loop pattern should we use to loop over the dice list and accumulate the number of winning number values we see? We can use the 4 die in dice pattern, for element in list, because we only need to examine each value. We don't need to change the list. So for die in dice, colon, and then we're only accumulating if the die matches the tavern keeper's die. So if die equals winning number, colon, next line indented, count plus equals 1. And I need to annotate that variable die of type int. Now let's print the count and the winning number after the loop to see how our algorithm does, and we'll run it a few times. Okay, we did pretty well. 3, 1, 0, 1, 1. Now let's implement the most wanted holder pattern. And this is very simple, the equivalent of finding the high card in poker. We'll just report the largest number rolled, and let's say you can win a consolation prize. Maybe you get to play the next round for free if you had the highest roll at your table. So we'll annotate a variable to hold the highest roll so far as we look at the dice you rolled one at a time. We'll call that highest of type int. Now I'll write a comment, find the highest die in the roll. Remember, with the most wanted pattern, we have to give the most wanted variable an initial value. There are two options here. One is we can give it the value of the first element in the list and then compare all other elements to it. The other is we can give it a value so that it will definitely be replaced by the first element in the list. So we know a die can't be 0, and we're looking for the highest die. So even if the first element in the list is 1, it will replace a value of highest that's 0. So we can initialize it to 0, highest equals 0. Now again, if we're just going to look at every element in the list, we can use the visiting pattern for die and dice colon. And then we need to compare if the die we're looking at is greater than highest. So if die is greater than highest colon indented highest equals die. Because now that's the largest die we've seen so far, and we'll want to compare the next die to that one. Let's print the highest and run this a few more times. And we can see it's always reporting the largest value in the list, regardless of where that value falls in the list. To test this thoroughly, we would want to hard-code our lists so that we'd be sure the algorithm works for the largest value at the beginning, at the end, and somewhere in the middle. We'd want to check a list of all ones to ensure it's finding the smallest possible highest value. Okay, that is a lot. I find that once we combine loops with lists, the topic of lists gets a little more complicated for most learners. I think that's because loops are still new. You will get this if you practice with it. I'm going to end this video here, and I urge you to practice with this. I've included some auto-graded exercises in the description of this video so you can practice writing the different looping algorithms and also the most wanted holder and accumulator algorithms. Once you've mastered the concepts here, you're ready to move on.